Abdul Jabbar, which he will present on synthesis and electrochemical characterization of nanomaterial metal oxides for high-performance supercapacitor. Let me introduce Dr. Abdul Jabbar Khan. Dr. Abdul Jabbar Khan is a nanomaterial scientist, highly skilled in material fabrication and characterization. He is also a researcher, educationist, and a speaker. He attained his M.Sc in physics from AJ&K University and MS in applied physics from Air University Islamabad. He completed his PhD in material science and engineering from South China University of Technology in 2020. His research focuses on carbon-based and metal oxide nanomaterials and nanocomposites for energy storage application, specifically supercapacitor. He has published 15 papers in peer-reviewed journals, 6 as first author and 9 as co-author, with a total impact factor of 54. He got his professional training on UV spectroscopy at Air University and X-ray crystallography and SEM at South China University of Technology. He is a CSC Scholarship holder for PhD by People's Republic of China, MS Based Award from Air University, and Excellent Poster Award by South China University of Technology at Innovation Day in China. Dr. Abdul Jabbar has delivered and presented different talks and presentations at national and international level. He has worked as lecturer in Army Public School and Colleges, head of physics department in Punjab Group of Colleges, and senior instructor in Government Higher School Secondary School Kahuta, with an experience of more than 13 years. We welcome you, sir. You can start your presentation now.
Thank you very much for inviting me to have some lecture. Okay, let me share my PPT. Okay, Bismillahirrahmanirrahim. Today my talk is about synthesis and electrochemical characterization of metal oxide based nanomaterials by high performance supercapacitors. I am here for Wind Power Pakistan Spring STM lecture series in 22 March. So my outlines is based on research and background, objective and approaches, results and discussions. So here we have synthesized 5 types of metal oxide materials for supercapacitor applications. We have alpha Fe2O3 hollow nanospheres. We have Fe3O4 Pani nanoparticles and FeO3O4 RGO composite, FeO3O4 RGO MO3 composite, and Cerium nanoparticles for supercapacitor applications. And then we will discuss about our conclusions and publications. So,
sir, can you put it on the slideshow mode?
I will. All slide like this. Is this okay?
On the bottom bar, you can see, yes, this one. I mean, press the icon. It's still not.
This one.
Okay, yes.
Yes, this one is okay.
Yes, please go on.
Okay. Okay. As you know, nowadays the energy is very important for modern society as well. So we need some type of energy. As the people are moving from rural area to the urban area, so the population is increased, due to which the demand of energy is increased. So we need some alternative ways of energy to utilize. So we are using the non-renewable energy sources and renewable energy sources. And also we have to use the green energy sources first. So we need some energy storage application, energy storage devices. So we can go for it, for these energy sources. So the supercapacitors are increasing with the passage of time. Its market is rapidly growing up, and a lot of people are working on it, and we find some good applications as well. So it's in every walk of life. You can see the supercapacitors are emerging right now in every area, and the scientific research is also increasing with the passage of time, and we have seen there are many types of supercapacitors are introducing and they are performing with the passage of time and meeting the requirement of the energy sources. So as we already knows about, some of people know about the supercapacitors. So because they have the high capacity electrochemical capacitors and capacitance values greater than 1000 farad at 1.2 volt, and they are the bridge between the electronic capacitors and the rechargeable batteries. And they are being preferred because they have the high power density and fast charging and discharging and long cycling stability and environmentally safe. So small, medium, and large scale applications are being used. So many types supercapacitors are using, like flexible and other types we will discuss later on. So there is a simple basic mechanism of supercapacitors. We have three components, like we have collectors and the separator, and then we use the EDCLs, and we will see how the charging is, how the ions are adsorption and deabsorption when we have some charging mechanism going on. So there are some different classification of supercapacitors. We mainly classified supercapacitors into three branches, like EDCLs, and they are also called double layer capacitors, pseudo capacitors, and hybrid capacitors. EDCLs are mainly consists of carbon materials, and the pseudo capacitors are mainly metal oxide and conducting polymers are being used for the pseudo capacitors, and then for hybrid capacitor, it is the combination of both pseudo capacitors and the EDCL capacitors mainly used for them. There are number of applications of supercapacitors are there. So from raw materials to single cell, and then we have a series of cells that can be utilized in different appliances, home appliances, hybrid buses, and aeroplanes, and boats, and in our mobiles and laptops, we are using the supercapacitors for energy storage applications. So there are different strategies to perform the supercapacitors. We have already discussed that there are some EDCL supercapacitors, the pseudo capacitors, and the hybrid capacitors. So we can use the mechanism of pseudo capacitors to enhance the capacitance and their properties in our research area. So what are objectives and approaches what to synthesize and make the supercapacitors? So we have prepared the supercapacitors for high specific capacity, and we want to enhance the contact area between the active material and the electrolyte. And then we have we want to improve the electrical conductivity, and we want to improve the number of cycles for least retention of that materials. So we have used the metal oxide for the metal oxide nanomaterials for our system. So because of them, because they have some properties like high electrical conductivity and high crystal stability, good chemical stability, and less volume expansion. They have redox chemistry and high capacity. So there are different approaches to improve the material synthesis of the supercapacitors. If we reduce the dimension size, we have to go for that, and the composite formations. And if we for the functionalization, we can improve the supercapacitor performance by controlling the morphology of the material during the synthesis. We can go for it, and then the encapsulations can be a benefit for the improvement of their capacitance, and for the modification of electrolyte, different types of electrolyte, and their controlled stability. We can utilize them for the synthesis for the desired results of our supercapacitor materials. So we have synthesized 5 type of metallic oxide supercapacitors, and we have we did some analytical characterizations and their electrochemical characterization. We'll discuss in our next slides. So here first we have synthesized the alpha halo nanospheres by hydrothermal method. We used the ultra fast method to prepare the halo nanospheres. We have used the hydrothermal methods, and by that method we have achieved the different types of morphology, and at the end we have used we got the halospheres morphology for our system. We have done some SCM and FPSCM for halo nanospheres, and with the variations of the time, we have changed we have got the morphology of our system halospheres. At the end, we have got the halo nanospheres, which were very important for the supercapacitor properties, because we have need a larger specific surface area to have the transfer of the charges. So we have done the TEM and HRTM of our halo nanospheres, and we have got we have done the SEAD and HRTM, and that correspond to our hexagonal structure of our system. And we have seen that the mapping which we have got from the STEM, we have find the uniform formation of our alpha halo nanospheres. We have done some analytical characterization like XRD and XPS of our halo nanospheres, and we have synthesized the we have got the XRD for our system that index to the matched peaks with our alpha Fe2O3. Then we have done the XPS spectra for the full waves spectra for our peaks. And then we have the Fe2P peaks for our system, and we have got some two satellite peaks for the Fe2P, and then we have got the OS spectra for our XPX, and we have found out the iron, metal, iron, and the hydrogen species are there in our XPS spectra. We have done the TGA, Raman, FTI, BET of our alpha Fe2O3 halo nanospheres, and again we have got the results, bizarre results, and we have got the Raman spectra for our alpha Fe2O3, which matched with the literature. So similarly, we have got the FTIR spectra for the our Fe2O3 peaks. And then we have done the BET to find out the specific surface area for our system, and we have got the BET spectra for this. Then we have done the electrochemical characterization of our Fe2O3 halo nanospheres, and we have done the CV for our samples, and we have got the pseudo-capacitive property of that our CV curves, which are in quasi-rectangular shapes, and we have done at different scan rates, and then we have got the GCD results for our sample, and at different scan rates. Also, we have got the specific we have calculated the specific capacitance of our sample, which was about the that is about different for different for maximum it is about 10, 40 and 530 and 325 for at the rate of 1.02 HE. And we have EIS spectra, electrochemical spectrum impedance spectroscopy, and we calculated our ESR and RCT values, and which was quite low, and which shows that our materials have shown good electrical properties. Then we have done the charge storage results for our alpha halo nanospheres, and we have done the anodic and cathodic current densities at different scan rates, and this leads to the linear relationship that gives the other our good characteristics of our materials. And then we have done the charge contributions for our system, and at different scan rates, and we have got the capacitive charge ratio, which was dominated over the diffusion ratio of our system. So we have compared all of these results. Then we have done the cyclic stability for our system, for our materials, and we have got the stability of our alpha halo nanosphere, which was about 98.8%, and after the 10,000 running cycles, and we have a regular pattern of our GCD curves for our system, and which shows that these materials have good stability. Then next we have done our Fe3O4 Pani nanoparticles by hydrothermal method, and we have prepared Fe3O4 nanoparticles, and then we have synthesized with the Pani materials, and we have got the composite of these two materials by the hydrothermal method. And then we have done some of their characteristics as well. So again, we have done the XRD, the XPS of our Fe3O4 nanoparticles, and we have seen all the peaks which are related to the iron and Pani composite. Pani, we have got all of the peaks related to the our system. Then we have done the TGA for TGA Raman, FTIR, and BET of our Pani nanocomposite materials. And we have again got the TGA with the maximum weight loss of that is about 195 to 287 and 337 for Celsius. And then we have got the FTIR spectra for our Fe3O4 and Pani and Fe3O4 Pani composite, and we got the desired peaks for our system. And similarly, we have done the Raman spectroscopy, and in Raman spectroscopy again we have got the related peaks for our system. We have done BET analysis for our Pani composite, and we have got the BET pore size width of about 10 to 40 nanometer, and the pore volume of that is about 0.045 centimeter cube, and the surface area of 83.89 meters square per gram. Then we have done SEM and TEM of our Fe3O4 nanoparticles. Again, we have got agglomerated Fe3O nanoparticles, and the Pani is to be wrapped by Fe3O nanoparticles, and we have some porous cavities as well, which are very good for the supercapacitor materials. And we have done the HRTEM and that indexed, that are the plane of Fe3O4 nanoparticles, which reveals that our synthesized materials was successful. Then we have done the electrochemical characterization again for our Fe3O4 composite, and we have got the pseudocapacitive CV types of curves, which were also related with the good capacitance. And then we have done the GCD for our iron oxide and Fe3O4 Pani nanoparticles, and we have got the specific capacitance that is about 16, 69 and so on, and we have the weight capability of that is 78.8%. And then we have calculated the capacitance that for Fe3O4 and Fe3O nanoparticles. And we have done EIS again, we have done the EIS curves, and we have calculated these ocean resistance and RCT for our sample. We have seen, we have done the charge storage results and cycling results for our system. Again, we have done the anodic and cathodic curves for our system, and we have got the linear relationship for this, and we have calculated the p values from our power rules, and we have got the capacitive charge and diffusion charge for our system, and then we have seen the stability about 25,000 cycles we have run, and we have got the regular pattern of our before and after the cycling test of our system, and which have shown the great retention and great stability of about 95 and 92% of our Fe3O4 nanoparticles. Then our third system, which we have the metal Fe3O4 RGO nano disk by hydrothermal method. Again, we have synthesized our Fe3O4 RGO nanocomposite nano disks by using hydrothermal method, and we have got the SCEM and TEM from this materials, and we have got the Fe3O4 nanoparticles, the HRTM. We have calculated their spacing and interplanar spacing, that is about 220, and which was close to the, which was about half Fe3O4 nanoparticles. And then again, we have done some of our XRD, TGA, FTIR, Raman spectra of our Fe3O4 RGO nanocomposite, and we have got the indexed peaks for our system. And again, we have got the desired peak for our FTIR and Raman spectra, and we have got the D and G band of RGO, which gives the confirmation of that the RGO is wrapped by our Fe3O system. So we have done the XPS spectra of our Fe3O4 RGO nanocomposite, and we have got the full wave spectra of our peaks, which are related with our carbon, oxygen, and iron elements. And we have done the Fe spectra, and that gives the iron Fe2P and Fe2P half peaks, which are related with the iron. And we have done for oxygen and carbons and all of the peaks which are indexed with our system. Then we have done their electrochemical characterization. Again, we have done the the CV curves for our system, and again they have shown the pseudo-capacitic nature of our system. Then we have done GCD curves, and again we have got some good specific capacitance for our Fe3O4 RGO composite, and we have got 1149 and 940 FG at current density of 1 with rate capability of 87%. Then we have calculated the specific capacitance of our composite and our iron oxide material, and then we have calculated their EIS spectra, and we have got the RCT and ESR values for our system. Then again, we usually have done the cyclic performance to check the stability of our materials, how our material be stable if we go for increasing the number of cycles. So we have seen the stability of our system that was quite remarkable, and it was about 97 point this one and 87 for the iron oxide. And again, we have tested the cyclic curves before and after the cycling test, and we have again got the regular pattern after these number of cycles. So we have next fourth system which we have synthesized, that is Fe3O4 RGO with MO3 by microwave method. So again, we have used the microwave synthesis for this system, and we have got the FGM nanocomposite material for our Fe3O4 RGO-MO material. Again, we have done some SEM and for this system, and we have got the MO3 and graphene layers in our system, and we have the atomic and weight per atomic percent and weight by percent. We have the iron, oxygen, and MO values are to be there in our system. Then we have done some TEM and HRTM of our system, and we have got we have got the NO and nanomaterials read by the graphene and iron oxide with the and MO3 with all the spacing, interplanar spacing, which are from related with our iron oxide and our MO3 materials. And we have again done the XPS of our FGM spectra, and we have got the iron, oxygen, and MO3D peaks in our system. And again, we have got the XPS peaks for our iron oxide, RGO, and MO3 system, and all the peaks which are related with the iron oxide and MO3 are present in our system. We have done the electrochemical characterization. Again, we have done the CV of our FGMO, Fe3O4, MO3. We have calculated the CV curve for our Fe3O4, MO3, and then we have seen the composite of our FGMO, and we have seen that the capacitance of our FGM system, that was about 1660, which was quite remarkable as compared to the other material. So we have seen the GCD curves for our FGM system, that was also very good. Then we have calculated the specific capacitance of our FGM, Fe3O4, and MO3 nanomaterials for our system, and we have got the different values for our system. Then we have cycling retentions for the system at about 5,000 cycles, and we have got the these type of retentions for our composite, our material Fe3O4 and MO3 materials. And again, we have done EIAS for FGM and our anodic and cathodic peaks for our system, and then we have done the charge capacitance and diffusion capacitance contributions to see how much charge is accumulated. So we have seen that the capacitive charge is about 55% as compared to the diffusion control process. Then last, we have done the synthesis of our iron CEO nanoparticles by hydrothermal method. Again, we have done cerium nanoparticles by hydrothermal method, and again we have used whatever the precursors, and we have used the treat with different temperature, and we have got the desired CEO nanoparticles, and then we have characterized these particles with their analytical property characterizations. Again, we have done with XRD, Raman, FTIR and NDX spectra for our cerium nanoparticles, and all the peaks which are which we have got from the cerium nanoparticles are present in the in CEO nanoparticles. So we have got the Raman spectra of our cerium nanoparticles and FTIR spectra, and we have done the EDX spectra of our particles, and all the peaks which are mentioned here are from the cerium nanoparticles. Then we have done the SEM, TEM, and BET of our spectrum, and we have got the TEM for our cerium nanoparticles, and BET for our cerium nanoparticles with BET pore size. I have mentioned all these value here, so I don't want to go in detail for these values. Then we have done some XPS spectra of our cerium nanoparticles, their full base spectra, and their CE3D and OS spectra, and all the peaks which are from the cerium nanoparticles are present in our cerium nanoparticles spectra. Then we have done the electrochemical characterization of our cerium nanoparticles. And again, we have got the CV curves of the pseudo-capacitive materials, and our GCD curves are with the pseudo-capacitive nature as well. So we have calculated the specific capacitance of our cerium nanoparticle, which is about 875 point this one. So with the rate capability as well. So again, we have done the EIS spectra for our cerium nanoparticles, and our cyclic stability for the cerium nanoparticle, which is also remarkable, and that is about 96.52%. So this is all about, we have done the iron oxide nanoparticles, we have done the Fe3O4 nanoparticles, we have done Fe3O4 RGO composite, and we all synthesize these materials by hydrothermal and microwave synthesis method. So here is the chart summary of our synthesized materials. For alpha halo nanospheres, we have specific capacitance of this one, and with number of cycles and the stability we have attained for this. We have published this article. Fe3O4 nanoparticles, we have got this specific capacitance and with this number of cycles, with the stability retention of this one. And again, we have published this one, FGMO composite. We have specific capacitance of this one, and we have the stability and retention. Similarly, FGMO composite, we have got the specific capacitance, and we have the stability retention. And cerium nanoparticles, we have got this type specific capacitance with a stability of about 96 point this one. So we have published our articles in Ceramic Internationals. Our C60 article is published in Material Science and Material Electronics. We have published the CEO nanoparticles in Journal of Electroanalytical Chemistry, and we have published Pani nanoparticle in International Journal of Hydrogen, and we have published our RGO wrapped Fe3O nanodiscs in Ceramics International, and we have published our hollow nanosphere articles in Applied Surface Sciences. Thank you very much. Any questions, please?
Thank you so much, sir, for your valuable lecture. If there are any questions you would like to ask, sir, please, you can ask questions.
I want to ask about the porous nanomaterials, because I am concerned that why porous nanomaterials are important for the capacitance.
Okay, because porous materials are important because if you have a porous material, then the charge can be accumulated in that, because we need a specific surface area for our materials. So more the specific surface area, more we can accumulate the charge. So that's why you can see in hollow nanospheres, we have synthesized for hollow nanospheres. In that hollow nanospheres, we want to accumulate more and more charge. Then we get the more capacitance. That's why we prefer the porous materials. For this purpose, we have calculated the BET to get the porosity and the specific surface area and their relative
Yeah, I have a
volumes.
question about the BET, that how much amount of sample you are using for that, and only solid sample we can use, or liquid sample can also be used for that?
Yeah. We have used solid sample for the BET, and it depends that if you have a small amount of sample, then you can also do the BET. So a very small amount of sample can also be utilized. It's up to the you that how much sample you want to go for it. So there is no any
No,
that
I'm not
you
asking
need.
about the amount of the sample. I am asking about the sample situation. Like if we have liquid sample, can we use the nanoparticles in the liquid form, or we first need to prepare in the solid form?
Yes, we know. We usually we need to prepare in the solid form. We have any after annihilation, after sintering, you can say you can go for the BET.
Oh, okay. So, you have tried uh, mm, uh, iron oxide and the selenium oxide, right? So, what do you think if we use silica oxide nanoparticles, or if we use some gold nanoparticles or silver nanoparticles with the fabrication of silica oxide on it, which has pores inside?
Yes, again, I said you that those materials which are porous, they can have a
Mm-hmm.
very good. They have a very good capacitance,
Mm-hmm.
because for supercapacitor we need to control two parameters. First, we must have a stability of that material. How much it is stable if we when we run that materials on number of cycles. If we increase number of cycles, we will see how much it gives the retention. So more the retention, more will be your material, more will be your material will utilize for the supercapacitors. So it can go for it because more the porous material you have, more will be your capacitance.
Okay, thank you so much.
When you talk about the stability, does the material itself is stable or it's stable when you used it in a supercapacitor? Like what actually you meant by the stability of the material? And in the end, you summarize that stability of this material is this much percentage. So what is actually meant by the stability and how much the stability is important?
Yes, actually, when you it depends on your synthesis process. Once you synthesize your material, after the synthesis, you will check that materials at room temperature for their stability. That how materials can withstand with the scan rate or with the with the scan rate, you can say. So we will see the material whether it withstand with the your scan rate. Once you increase the scan rate, can it fluctuate? Can its curves will fluctuate or not? So this is what we have. So it relates with the your preparation is very important for the stability point of view. If you synthesize such a material which cannot be stable, means which cannot be utilized in a stability way, so you cannot go for it. So you cannot make a good supercapacitor.
Okay, thank you so much. Are there any other questions that anybody would like to ask? Okay, I think there are no more questions. Thank you so much, sir, for your valuable lecture and for giving us time.
Thank you
Thank
very
you
much.
so much for your time.
Thank you.
Okay, now here we will end this session of our. I hope you will get an insight of the Dr. Jabbar's research. And if anybody wants to contact him, you can contact him via through Women Power platform, or you can contact him directly. So thank you so much, sir.
Okay, okay. I want to add one thing. So yes. Thank you very much to Dr. Tabassum and her team that are doing a very good thing, and you are conducting some sessions to introduce the research, which is very important and very good thing. So I like this the way you are going. So keep it up.
Thank you so much, sir, for your valuable feedback.
Okay,
Okay,
thank you.
take
Okay,
care, everybody. Allah Hafiz.
Hafiz.